Hi everyone, so today we're going to talk about Thevenin equivalent circuits. So by the end you should hopefully be able to take a resistive circuit of the type we've done before, that is multiple sources and so on, of any size, and reduce it to a Thevenin equivalent form. Now Thevenin equivalent circuit, even though it's named after Thevenin, was actually formulated by a guy called Hermann von Helmholtz, but Thevenin popularized it, and so he is the one that gets the credit. Basically this says that any linear electrical network could be simplified to a single source and single impedance, and this is useful if you're going to replace components in a system. You don't need to recalculate the whole system, you could just do some simple calculations. So to give you a better idea of what that means, you could have, say, a system with any number of components like this here. This is just a black box. Well, it's not black, it's some other color, but you could have any number of components connected in any configuration. So you could have thousands or millions of these components, sources, resistors, whatever it is, as long as they're linear components, and then you could convert that to just a single source and a single resistance. So if once you have these, then what the Thevenin theorem says is that if I connect some component here, the voltage across it and the current through it should be the same as if I connect it here. And it doesn't matter what this resistor is, it will always work out to the same value of voltage and current as if I connected it to this simplified circuit here. So you could see if you had this resistance changing, instead of going and recalculating, say, 1000 by 1000 matrix every time this resistance changes, it's much simpler to just calculate it here with this one resistance. So that is the power of the Thevenin equivalent form. So as you can see from the diagram before, we essentially had to figure out what the Thevenin voltage was and what the Thevenin resistance was. So we have these two things that need to be estimated, or calculated rather, and the method to do this varies depending on the type of sources that we have in the circuit. So we could have independent sources only, we could have dependent sources only, or we could have a mix of independent and dependent sources. So we look at these three conditions and see how we calculate the voltage, the Thevenin voltage and the Thevenin resistance in each case. So if we have independent sources only, then to find the Thevenin voltage, what we need to do is remove the component that we're looking at, the component that we want to change, remove it from the circuit, and then find the open circuit voltage across the nodes that we removed it from. And we can find this using superposition or nodal or mesh analysis, whatever it is. And the Thevenin voltage is equal to that open circuit voltage, sorry. And then to find the Thevenin equivalent resistance, Z Thevenin, which is the impedance, or R Thevenin, which would be the Thevenin equivalent resistance. To find that, what we do is we open circuit all current sources and short circuit all voltage sources. The same thing we did with superposition. We turn the sources off, and then we find the equivalent impedance looking into the circuit. So let's do an example now and see what all this looks like. So the first thing we do is we want to find the Thevenin equivalent looking into the nodes A, B. And you'll see I've marked here RL as the load resistance. That is the resistor we want to take out from the circuit. That is the component that we're interested in changing. So the first thing we do is we remove it. So you'll see here I removed RL and I have my two terminals here. Then what I'm going to do is I'm going to find the open circuit voltage across these terminals. And I'm going to do it by the theory of superposition in this case. I could use any of the theories, but I'm going to use superposition in this case. So I have, if I use superposition, taking the 10 volt source first, I would have to short circuit the 12 volt. And I would have 5 and 5, and the voltage here would then be 5 over 10 multiplied by 10, which is my voltage divider equation. And similarly, if I did it with the 12 volt source, I would have to short circuit the 10 volt, and then I would get 12 and half of 12, which is this, would give me 11. Now I could do it other ways as well. I could simply say I have 12 volts here and 10 volts, therefore the current would be 12 minus 10 on 10, which is equal to 0.2 amps. And then if I have 0.2 amps, the voltage drop across here is going to be 0.2 by 5 is equal to 1. And then since it is 1 volt in this direction, I have 12 volts, 1 volt drop, I get 11 volts. So any way I want to do it, I should get the same thing, and I could use nodal analysis, loop analysis, it doesn't matter. So that gives me my open circuit voltage, which is equal to V Thevenin. So that is one of the components. Then for the next one, I turn off all the sources, which means I short circuit both voltage sources, and I have to find the Thevenin equivalent resistance looking into the circuit at this point. So what would be if the resistance here, if I put an ohm meter at this point, then what am I going to get if I measure the impedance from this point? So if I look at the arrangement, it is 5 in parallel with 5. So if that is difficult for you to see, sometimes you look at it and you think that, well, these two look like they're in series. But remember, we're connecting from this point here. So if I take these 2 points A and B, and I draw a line like that, then I could say this resistor is connected from A on this side to B on this side. And this resistor is connected from A on this side also to B on this side. And I would get that. That is because I'm looking in at that center point. So this and this is the same configuration. So here I think it'll be easier for you to see that these two 5 ohm resistors are in parallel. And you could always redraw the circuits like this if it's easier for you to see. So the equivalent resistance is 5 in parallel with 5, which is product over sum. So 5 by 5, 25 over 10 gives me 2.5 ohms. And now I have my Thevenin equivalent resistance. So if I wanted to solve for the circuit, say putting in any resistance, the one we used all the time was 5 ohms, then I could put in my 5 ohm here with my Thevenin equivalent, and I could find the current would be 11 over 7.5 is 1.4667 amps. So, and if I wanted to find the voltage would be 11 multiplied by 5 over 7.5, and that should give me, if I remember correctly, I think it was 7.33 volts. So, but you could just double check that to make sure. So this is the same thing that we got before. Now imagine if we wanted to change this 5 ohm to a 10 ohm resistor or 20 ohm resistor or any other resistor. If I didn't have the Thevenin equivalent, I would have to go through the whole process of superposition or the whole process of nodal analysis. Whereas if I have the Thevenin equivalent, then all I need to do are these simple calculations now to change it any amount of times that I need to. So that is what we do for the independent sources. Now moving on to the dependent sources. What we do for the dependent sources, since dependent sources maintain the voltage or current based on some other value in the circuit. If there is no excitation, if we have no independent sources, then the dependent sources are going to have a value of 0. So it's similar to a passive component in that way. And the Thevenin equivalent circuit looks like that. So you'll see that when we find the Thevenin equivalent, it is going to come up like that. Or if you wanted to draw it another way, you could draw it just like we had the Thevenin equivalent before, and you would get 0 volts here plus V Thevenin. So these two, R Thevenin. So these two are the same. So how do we find R Thevenin if this is the case? We can't, as it turns out, do it the way we did it before. So we can't just short circuit all the dependent sources and then get the equivalent resistance, because the dependent source, as we just discussed, behaves sort of like a passive component. So we can't take it out of the system. So what we are going to do, since we need some excitation to make the dependent sources work, we are going to insert a voltage source or a current source, anyone you want, into the part that we took out the component from. So what we're going to do is, when we remove the component, we're going to place a 1 volt source there and measure the current. And then once we have 1 volt and we know the current, that ratio of voltage to current is going to give us the resistance. So this is an example we have where this is the terminals. I've already removed the component. So we have a dependent source. We have no independent source anywhere in the circuit. So what I do is I place a 1 volt source here between those terminals, and now I'm going to measure, well, not measure, but calculate the voltage, current coming from this source. So what I could tell right away is that I1 here, if I have a 1 volt source here, that the I1, which has this 1 volt across it, is 1 volt over 4 ohms, 0.25 amps. I know that the voltage here is 5I1, so that is 5 by 0.25 will give me 1.25 volts. So then I2 will be 1.25, which is this value here, 1.25, and this is 1 volt. So this I2 is 1.25 minus 1 over 5, which will give me 0.05 amps. So if I then add, I want to find this current here, remember that is my aim. So this current there will be I1 minus I2, which will give me 0.25 minus 0.05, which will give me 0.2 amps. So if I have 0.2 amps here, that is 0.2 amps going through the 1 volt source. It means the equivalent resistance that this source is seeing is 1 over 0.2, which is 5 ohms. That is, this source, this 1 volt source, this 1 volt source only sees 5 ohms, regardless that we have all these different things connected here. It's delivering 0.2 amps. So for all it knows, it's a 5 ohm resistor, because there's absolutely no difference between having a 5 ohm resistor here to having this entire circuit. And once I have that, that is my Thevenin equivalent circuit here, 5 ohms. And that is all we do for the for the dependent sources in the circuit. So moving on now to sources with circuits with mixed source type. So we have both dependent and independent sources. Now what we need to do is we need to find the resistance. So Z Thevenin here is the impedance. You could use that also. So R Thevenin, if you have a resistive circuit, the Z and R are the same. Z is more general because it takes into consideration inductances and capacitances and so on, and we'll do those later on in the course. So if we have the mixed source types, we need to find both the open circuit voltage and the short circuit current, and then this open circuit voltage is going to be our V Thevenin, and the ratio of the open circuit voltage to short circuit current will be the Thevenin resistance. Now this is a very general method, and you could actually use this for all the other methods as well, but it would probably be longer because you have to not only do one set of circuit analysis for the open circuit voltage, but you have to do another set for the short circuit current. Whereas if you just look into the circuit, you could probably quickly find what the equivalent resistance is by looking in. So or if you have the dependent sources, obviously you can't do this because you can't open circuit the terminals because you have to insert the resistance. So you could use this for the independent sources as well as the mixed sources. So let's go through an example now. So we have a 10 volt source, which is our independent source, and we have here our dependent source, and I've opened these terminals here already. This is where our component would go, and the first thing I'm going to do is I'm going to find what the open circuit voltage is. So I have to find the voltage here. So I need to do that by determining what the voltage of the dependent source is. So I'm going to start, the voltage here is dependent on I1, so I'm going to find that I1 is 2I1, which is the voltage here, minus 10 volts over 10, which is the total resistance here. So that will give me I1 is equal to 2I1 minus 10 on 10, and if I go through that and solve it, I'll get I1 is minus 1.25 amps, which simply means there are 1.25 amps going in the opposite direction. So now using that, I could find the voltage, because I know that if I1 is this way, then the voltage drop will be this way. So the voltage across here will be 5I1, which will be 5 by minus 1.25, that is negative 6.25. So 10 volts, and it is increasing this way. So 10 volts, and it increases by negative 6.25, which essentially means it decreases by 6.25, which gives me 3.75 volts. So that is my open circuit voltage. The next thing I have to do is short circuit the terminals. So here I short circuited the terminals, and I have to find again what is the value of this short circuit current, and I have labeled it here IN. You might be wondering why IN. That is because we call it the Norton current, and we'll look at the Norton equivalent circuits after the Thevenin equivalent circuits. But just like the Thevenin voltage is the open circuit voltage, the Norton current is the short circuit current. And I'll show you how to change between the Thevenin and Norton forms. So don't worry too much about it now. So now I'm going to find again now the Norton current. So I need to find I1 to figure out what this the value for this dependent source is. But first I could find I1 by just simply looking at the 10 volt source. Now this point, since it's short circuited, is 0 volts. So I have I1 is 0 minus 10 on 5, which is minus 2 amps, which means simply that 2 amps in this direction. And since this is minus 2, then this voltage here will be minus 4 volts. So I2, which is in this direction, is minus 4 over 5, which is minus 0.8 amps in that direction. So the Norton current now is 2 amps in this direction minus 0.8 amps, or 0.8 amps going, if it's easier for you to see, in this direction. So 2 amps going in this direction minus 0.8 amps, which will leave 1.2 amps in the going through the Norton short circuit. So now I have 1.2 amps is my Norton current, and I can find my equivalent resistance by the open circuit voltage on the short circuit current, which gives me 3.125 ohms. So I could use my open circuit voltage and my equivalent resistance and find what my Thevenin resistance, my Thevenin equivalent circuit is. So to summarize, we looked at Thevenin equivalent circuits into a pair of nodes. Sorry, we didn't do the Norton equivalents yet, so just scratch that off. And this included circuits which are independent sources only, dependent sources only, and mixes of independent and dependent sources only. So what I would like you to do is just make up a table like this one, and for independent, dependent sources, for the different types of sources, what you're going to do is just create a summary sheet where you say what is the method to find each one. So for instance, for independent sources only, you could write here that V Thevenin is equal to the V open circuit, and for dependent sources only, V Thevenin is equal to 0, right? Or you could say no source in the circuit. Good. So the next time we will do Norton equivalent circuits.